welcome to the lecture of linear algebra. In this lecture we will talk about eigenvectors and linear transformations. Uh, and the goal is to understand the transformation x to x and how the eigenvalues of A and the eigenvectors of A can be used in the transformation by A. I mean, we have already discussed so much about transformations in our previous lectures through A, um, and we're going to use we're now going to use the eigenvectors of A to assist in actually our linear transformation. I mean, we will use the concept of similarity here, where A is similar to D, and D may be I mean, D, like in the last lecture, it may be diagonal, it may not be diagonal, but we will be developing understanding of the transformation that could be achieved by A and the correspondingly by D, and how they relate to each other, right? So in general, uh, if you remember from our earlier lectures, that if there is a space, a vector space V, which is an, let's say, an n-dimensional space, and that WB actually an m-dimensional space, and correspondingly T is the linear transformation uh, such that basically T converts the vectors in V to W. Okay, so to associate a matrix T, we choose that let's say B is the basis of this basis for V, and let's say C is the basis for W. Okay, now the point here is that we can say that at any point, let's say in X, and let's say this is V, right? This is a subspace V. Any point X in let's say X here, it could be transformed to a point in this space, let's say W, and to the point here somewhere, let's say here, and let's say this is we know that this is Rn is an n-dimensional space in Rn, and this is, let's say, m-dimensional space. So what does is basically this vector T transform this V to W, and of course if B is the basis for V, then it means any vector X, if let's say this is X here and this is T of X, that transform this to W, this any vector X in V can be represented in terms of any basis of V. Let's say these bases can be written X of should write as X of B. Okay, and similarly this can be represented in T X of C. Yeah, so we may so in V we choose the basis set of vectors as B, in W we choose the basis set of vectors as C. So if any point in X in V has to be represented in the corresponding basis B, we can write it as X of B, and we know that how we have done it already. We have studied a lot about that in basis and change of basis, and and similarly we transform with T, and this will go into W, which is an Rm space, and we can win any if we choose any standard basis for C, for W, which is C, So we can transform this the resultant point t of x in terms of the basis c. So I mean, it depends on the choice of b what you are having, right? I mean, so since you can have multiple bases for the vector space v, so if there isn't the space b prime, then this x can be represented in terms of b prime, and we have already seen that how actually we do change of bases. um, we can how you actually carry out change of bases, right? So so the idea here is, um, uh, so again, T is the transformation from V to W, and we know that from our earlier discussion that yeah, in our previous lectures, that any point x can be written in terms of its standard basis, which is R1 times B1 plus R2 times B2, and R, because it's an n-dimensional space, so it is Rn times Bn, and B we know is nothing but B12. Bn are the basis vectors in this basis set B, right? So it means x of B, we know that can be written as R1 to up to Rn. Okay. Now, since we are going to transform this x into to t of x, right? So it means it's a linear transformation. So if from that equation which is here, t of x, actually I can write this as transformation applied to r1 b1, r2 b2, and rn bn, and I can move, because linear transformation, I can move that in. It becomes r1 t into b1 uh, plus, okay, let's get rid of that for a moment, plus r2 t of b2, and plus rn into t of bn. Okay, should be writing like that, curly bracket. Okay. Now this vectors, when x here in this point can go to t of x in this point, but the problem here is that in W, these are not this t of x is in terms of standard basis, which is, let's say, if it's three dimension, this is 1 0 0 0 1 0 and 0 0 1, but we have already defined a basis vectors for that as c. So what we want to do is to convert this t of x that we have got in W to the basis vector c. So it means, if I say this tx of c, want to convert the tx of c, that means R1 should be this transformation should be represented in terms of C. This should be represented in terms of uh, C, and similarly Rn T Bn should be represented in terms of C, right? So it means that if I want to have convert this uh, convert this thing here from from uh, from V, from the basis set in V to the basis set C in W, I can write this as Tx of uh, uh, C is nothing but equals to T B1 and C, again T B2 in C, and T Bn in C, and I can write this as R1 R2 up to Rn. Now this is called, because these are vectors, b1 is a vector, so transformation is also a vector. This is a vector, this is what transformation is also a vector, this is also a vector. So it means that it will form a matrix which is M, and we'll talk about dimension here, right? And then M, and this we know that is from here is nothing but x of b, right? So uh, this is a transformation that any point in V, which is x, right, has to first represented by is represented in terms of the basis of V, and then it has to be transformed to t of x, and that resulting point has to be represented in terms of the basis of that uh, vector space, which is actually the basis of which are actually C, right? Now this matrix xm is M is called uh, uh, called the matrix for t relative to the bases b and c. Okay, so this matrix for t relative to the bases b and c, this M is called uh, this matrix, right? Now if you want to see that in in the terms here, so this is the sequence of steps that we just did to cover that, right? So it means starting from a point x which is in v, first we have to represent that in terms of its basis, which is x of b, right? Or okay, and then what you have to do, you have to apply this M matrix here to convert them into the transformation Tx of C. And similarly, if you want to move it to simply T of X, right, okay, then you can go from here, or similarly I can go to here, right? So if I multiply this by T, then I will get here X will move to T of X, and I can move this T of X to the basis Tx of C, and similarly x of b is represented in terms of basis b. It has to be multiplied by m to convert it to tx of c. Okay, now this is how this uh, whole thing of linear transformation works from the point of view of the basis. Now, now let's say that if suppose uh, B has two basis vectors, which is b1 and b2, uh, and actually let's say this is the basis for v, and let's say three vectors, which is v1, v2 and v3, which is a basis for w, uh, and we have transformation t, which converts v to w. uh, the property then the property that t of b1 is will be, let's say, 3c1 minus 2c2 plus 5 c3, and tb of 2 is equals to 4c1 plus 7c2 minus c3, right? So we already have done covered that kind of thing in change of basis, but here luckily we've been given here that there are certain vectors in basis for v. Luckily here we have given that there are two set of vectors in b, and there are three set of vectors in C, and we were also given the transformation of these basis vectors in terms of basis vector of b's in terms of c's, and similarly so on and so forth. So it means remember that we have uh, m as, remember, is nothing but tb1 of c up to tb2 of C, right? So in that case, we can simply see here that M is nothing but will be equals to uh, 3 minus 2 5, corresponding the coefficient of these vectors C1, C2 and C3, and similarly here 4, 7 and minus 1. Okay, so this is the M matrix. This is a matrix of for T relative to the bases B and C, right? So so we can actually apply this M matrix to transform the point x uh, in with in space V to corresponding to the point in in W with a basis C. Okay. Now similarly, there could be a scenario in which you are transforming There could be a scenario in which you are transforming uh, within a space. So linear transformation from V into V, right? So if you are transforming uh, vectors within the same space, so uh, we can say that W is so from extending the concept from the previous examples, so we can W is same as V. We can think of now W as same as V, and the basis C is same as B, right? So the matrix M in this case will become matrix for T relative to B, because now we only have one space. Now these are uh, so as I told you that V is equal to W and B is also equal to C, so it means there is no C involved here. So it means the matrix for T relative to B can now be easily written as T of B, right? So we can now think of T of B, and the beta matrix, which we actually say that T such that V that will transform the points V into the same points in V is actually nothing but, from that previous knowledge here, is nothing but equals to T of B and X of B, right? So you remember this here, this equation, this matrix here. So because B and C are the same, so Tx of B, which is here, right? And now this T of B, which is now equals to M, you can think of M, that transformation matrix has to be now represented in terms of the basis B. Okay, transformation matrix now has to be presented in terms of basis B, right? So this is quite important. You have to really understand this, that this transformation matrix has to be represented in terms of B, right? So this is matrix for T relative to B. So this becomes uh, matrix for T relative to B, or it is often referred as the B matrix for T. That means the T matrix has to be in the basis uh, B. Okay. Now let's do an example to illustrate that what we have just said. That, let's say for example, transformation is A naught plus A1t plus A2t square. Okay, is given by A1 plus 2A2t, right? And this is the transformation that we know is actually you can think uh, of as T, and this is general polynomial space P2 to P2, right? And you can think of this transformation nothing but as the derivative here. Okay, so you can think of this transformation that takes a vector and to find out its derivative with respect to the independent variable. In this case, the independent variable is T. Now what you have to do is to find uh, find the beta matrix for T, because when beta is 1 T and T square, so it means because the order of the polynomial is the same, the space is the same, so we have to find the beta matrix for T here when beta is equals to 1t and t square. So first thing that we have to do is to find this T of B. It means you have to represent this transformation matrix in terms of B, right? So the transformation matrix in terms of B can be written, you can think of this as that you have to first find the images of the basis vector, right? So it means, so this is the basis vector first, so if I put 1 here, it means it will derive with respect to time, the answer will be 0, right? And now similarly, if I put t here, derivative with time, that will be 1, and if I put t square here, the answer would be 2t. right? So it means this will be the transformations of the basis vectors. You can think of beta matrix for t. Remember this is the beta matrix for t, right? So we have just found out that this is the meta this is t of 1, this is t of t, and this is t of t square, and this is the images corresponding to these bases, right? Now we have to represent those images in terms of b, right? So it means if I want to write t1 of b, which I say that here will be nothing but, because it's 0, the answer will be 0, 0 and 0. What would be tt of b is nothing but equals to 0. What would we think is 1, sorry, 1, 0 and 0, because the constant is 1 here. Now t square in terms of b is now 2t. So the first thing here will be 0, this will be 2, this will be 0. So it means the M matrix with respect to B, or beta matrix for T, will become as T of B as 0, 0, 0, 1, 0, 0 and 0, 2, 0. Okay. Now second part that you say that verify that T of P into B is nothing but T of B into P of B. Now for each P in P2, for so any vector is P in P2, it means it can have the following component, which is P of T as a naught plus a1 t plus a2 t square. So 1 t t square are the bases, and now it's got here two dimensions, a naught, a1, a2 are its coefficients. So we can say that P of T into B is nothing but equals to a naught, a1, sorry, yeah, a naught, a1 and a2. Now the transformation of T of P into B, we know that will be what is nothing but you have to first derive it and then express it. So it means if I do the transformation first here, which is now will be a1 plus 2a2t. Now if I represent that in terms of bases, that means that will be 0, a1, oh no, sorry, a1, 2a2, and then of course 0. 1 bases are, remember, this is 1 t and t squared. So if you look at from here, corresponding to unity, you have a1, corresponding to the to t you have 2a2, and for t square you have nothing. So it means a1, 2, a2 and 0. So what we have now is tp of b should be equals to 0, 1, 0, 0, 0, 2, 0, 0, 0 with a naught, a1 and a2, right? The formula which is written over here. So if I multiply that, that becomes a1, that becomes 2a2, and that becomes 0. So this is equal to that thing here. So it means we have just proved that that this transformation exists. So what you have to do is to find any transformation within a space has to be governed by the following formula, right? So now if I make a diagram of that to make you understand that what we have did, uh, you can think of this as now so so you can think of this as uh, r cube, and that is leads to a point in this, let's say this is corresponding to P2 here, and the same way the intercept a0, a1 and a2 is the intercept of, let's say this is the basis 1 for example. Let's loosely say this is for t, this is t squared. The point will be lying somewhere a0, a2, so point will be somewhere um, let's say uh, here in that space, and the corresponding d in the subspace, let's say a0 plus a1 t plus a2 t square. The corresponding d, the point, this point which is p will be uh, in the basis set of vectors uh, b, and then of course I will have the transformation t by this matrix, which is somewhere going here, which is uh, a2 plus 2 a2t, sorry, a1 plus a22t, and of course this is also uh, subspace R3, and this is now the point here, which is in terms of the basis of that same thing here, a1, 2, a2 and 0, and this is by t, right? And of course this is the point a0, a1, a2, and this point has to be transformed to this point by t of uh, t of p, right? So you can think of this point as uh, x. I mean, if you want to say x, or in the context that we are saying this is p, this is p of b. Now this is your uh, 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 t t of p2, and this is your point as t of p2, t of p, p2, t of p in terms of basis b. Okay, so you can go from here and then you can represent in terms of the basis here. So so in so once we have know that two things here, that if you are transforming from different bases, it means um, tx of uh, uh, c is nothing but equals to we know that is tb1 of c and tbn of c, and you have this as x of b, right? Or you can also say this is mx of b. Now but if you are doing within the spaces, within itself, I mean it is from v to w, right? So we have got different basis basis vectors or different subspaces. Now but if you're doing that transformation within the same space, so it means resultant vector is also in the same space. So it means the point that we are actually um, getting here is also will be more like this, that this transformation in terms of t of x into b is nothing but t relative to b and x relative to b. Okay, now this is beta matrix for t, this is the resultant vector here. So in this scenario, this is the point that we are looking for. Now so generally in problems that involve applications of certain sorts. Uh, so transformation first appears as something like this, that you transform vector x to a of x. So in a sense that uh, so you normally know that this is actually t of x, right? So so if A is diagonalizable here, then there is a basis B for R of n consisting of eigenvectors of A, that we already discussed in our previous lecture. That so if A is diagonalizable, then it means all its eigenvectors should span should be able to span Rn. So if A is n by n matrix, A is an n by n matrix, corresponding lambda vector correspondingly eigenvectors v1 to vn should form the space the basis the eigen basis for Rn. Okay. Now, similarly, corresponding eigenvalues could actually form the eigen subspaces, right? So, so in a sense that if A is diagonalizable in this scenario, then there is a basis B for R of n, as I told you here, consisting of eigenvectors of A, right? So that we'll show that in a short while that if the beta matrix for T is diagonal, right? So in that case, the beta matrix for T is diagonal, right? Because what we are saying that because if A is diagonalizable, then A can be written as something like in a form like this. So it means uh, the the D here could form the basis uh, for could form the basis sorry could form the beta matrix for transformation, beta matrix for transformation, which is actually diagonal. Okay. Now suppose that A is equals to PD P inverse, um, and let's say D is a diagonal matrix which is also happen to be an n cross n matrix, because P has n eigenvalues, so it means it's also n cross n, and P inverse would also n cross n, so all have to be n cross n. Then if B is the basis for Rn, which you can find in vector P, and formed from the columns of P, then D is the beta matrix for the transformation x to A of x. So it means um, what we are saying in the context of thing here, that is, remember we just talked about that a transformation within the same space, right? Transformation that V to V, right? So we found out that transformation matrix is in that scenario resulting is something as a formula which is like that. So this is the beta matrix relative to T, right? So we are saying that if A is diagonalizable, this D matrix is the transformation from can result from transformation to x of x, and this T of B is actually D, uh, D, right? So if we can actually prove that by saying that if columns of B are columns of P actually columns of P are actually B1 up to Bn, and so that B is equals to B1 up to Bn, and P of course will also is already there. So P is actually we are saying that P is actually the change of coordinate matrix PB, right? uh, as we discussed earlier, that you know that x of is equals to P uh, uh, P of B into x of B, right? So as we discussed in our previous change of basis equations, that uh, it exists such like that. So it means normally you don't write P here like that, so it's just right here as x is equals to P times x of B, right? Okay. Now, and P must be the basis vector containing P must be the matrix containing the basis vector of B. Okay. Now it means that P times x of B, x of B is equals to x, and we know that from our discussion that x of B is nothing equals to P inverse of of x. Okay. Now in this case we know that T of B is nothing but equals to T of B1 from our discussion a while ago, that you can write this as like this. Okay. Now because T of B1 is nothing but equals to A times B1 B, and similarly A times Bn and B, this can be written as, because A is a similarity matrix with respect to similarity matrix, we can write this as multiply it on the left hand side by P inverse. You can actually get here is P inverse A times B1 and P inverse A times Bn. So it means I have simply applied this identity here and applied by P inverse. When I applied by P inverse here, it means this point actually get converted into can you can remove the basis from this point, and actually can reveal uh, 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 the column in standard basis. Okay. Now this can be written as nothing but equals to P inverse A, you can take it out common, which is B up to Bn, and this becomes out to P inverse A times P. So the transformation matrix for B can be written like that, right? Now, so I think I should get this out here. Now, since you remember that A is equals to nothing but P D P inverse, right? And A is similar to D. Similarly, remember that D is equals to nothing but can be written as P inverse A times P, right? So it means if you look at those two here, we can easily see uh, that your T of B is nothing but equals to D, right? So let's sum up what we have just said so far, and so you can get your head around this thing here, right? So what we are saying that so far now, that we can use eigenvectors uh, for linear transformation. Okay, for linear transformation from one space to another space, right? We have discussed about this linear transformation in our previous lecture at length. So to give a summary of that, so we say that there is a vector space V and there is a vector space W. V exists in R of n, W exists in R of m. Okay, V has the basis of B and W has the basis of C. Okay, so any point x here, actually, if I apply the transformation T of x, which is sometimes can written, which is actually written as T times A of x, it means x will transform into another point in W. Okay, so this is Rn, this is Rm. Okay, so it means the dimension of A could be, if both are Rn, the dimension of A is n by n, right? Or if Rn to m, so it means the dimension would be m cross n. Okay, so this matrix A T of, let's this call this T of x. So any point x will actually move to t of x in space W. Okay. Now, and of course you have to multiply with A with m cross n matrix. Now, because this x is in the standard basis, okay, standard basis we know that is nothing but 1 0. So if for 3 dimensional standard basis is 1 0 0 0 0 0 1 0 and 0 0 1. But the thing here is you have already defined the set of bases for this vector space V. So it means this x has to be represented in terms of x of B, right? And we know that to find out x of B, we have to do is P inverse times x, right? Where P is the vector that contains the basis vector B up to Bn. Okay. Now, so it means this x now has to be presented in x of B. Okay. Now, and when this is transformed to t of x, I want this t of x to be in the basis tx of this vector t of resultant vector t of x in terms of the basis C. So it has to be presented in terms of C. So t of x has now to be represented in terms of the basis C. And we know that we can apply similarly the same thing here, that we know that this t of x and this tx of C, so it means this tx of C, the resultant vector here, should now be multiplied by, let's say, this vector q, okay, and this is your t of x, and q now is the set of basis vectors, actually that will be q inverse, sorry, q is equal to c1 up to cn. So this is a matrix which contains now the basis of this vector space W, right? So this is actually what our real problem is. Okay. So the point in x in vector space represented in the standard basis has now to be represented in x of B, and now when you transform this x into t of x, it has now to be converted to tx of C. What we are doing is developing a relationship between this x of B and this tx of C, right? And we have done that, and we found out that you can do that. Means you can define this, you can see the lecture again to see that this is the transformation, that any point, transformed point, can be presented in the basis C by using the M matrix, which is the matrix for T relative to basis B and C, and this is your x of B. Now, the thing here is sometimes this is the expression that deals with transforming points from one space to another space, but there may be scenarios in which in which the points have to be transformed in within the same space, right? For example, the case of shear transformation, for example, or simply the rotation. It means uh, actually the transformation is happening within the same space. It is not changing dimension of the space, right? So in that scenario, it means now there are not two spaces. There is not a single space. So it means you can think of now W is same as V. It means the basis vectors for that one, let's assume for a moment, is also the C or also as equals to B. So in that scenario when we're transforming from V to V, it means again the problem remains the same. Any point in x, right? Any point in x here, say for example in this scenario this is V and this is again the V, right? Now any point P in here, uh, P here, uh, any point P here, okay, has to be transformed to T of P. But thing is this point has to be represented in terms of basis vector B, and this transform point has to also be represented in terms of the basis vector B. Now again this equation here tells us that relationship that Tx of B can be represented as T of B and x of B, and where T of B is nothing but equals to, we know that the thing here which is T of B1, same thing here, which is same formula again, T of Bn in terms of B, right? So you can use that to find out this problem, that we develop a relationship between this point and this point over here. So we did an example for the polynomial scenario, in which the transformation was actually the derivative, and we saw that how we actually first finded the images of the bases 1t and t squared, and represented that images in terms of the basis, right? We take the basis vector, find their images under the transformation, and then represent those transformed bases, those transformed bases, or let's say the images of those bases in terms of the vector space B. This gives us this as of the transformation. Remember that this gives us the transformation of the resultant points over there, and you can use that T of B and x of B, which you can easily find, to find out the point Tx of B in here, or we can say, you can, given this point, you can actually find this point. Okay, now this is the discussion that we had earlier, right? Now what we are proposing to you now is that this transformation actually, which is x to ax here, right, we can say that it is quite easy to find in the case when you are transforming from V to V, that if you find a similarity transformation of A, which is P D P inverse, right, we are saying to you that P is actually and D here, and P inverse are the three matrices. We say that that in a V to V transformation, please listen carefully, in a V to V transformation given by a matrix A, right, we have to find, remember this, we have to find this beta matrix, which is, this is T of B. We say that the diagonal matrix is the beta matrix. If you carry out similarity transformation, this diagonal matrix is nothing but the beta matrix within V to V transformation, within V to V transformation, and P is the change of coordinate matrix from X to XP. We are saying that P, there are two very important things. D is the beta matrix for transformation from V to V, and P is the matrix that is change of coordinate matrix, which transform X to X of B. It means we, as I told you, that P is the change of coordinate matrix X of B. That's what we are going to prove, that if A is a matrix, its similarity transformation is PDP inverse, then P is the change of base matrix. D is the beta matrix for T. That's what we are going to prove. So it means if T of B, as we already know, can be represented as, from our general discussion earlier, T of B1 has to be in terms of B, and T of Bn in terms of B. So it means that AB TB or T of B1 is nothing but AB multiplied by B1, and T of Bn is nothing but AB multiplied by Bn. Now this has to be written in terms of B, in terms of basis vector B. Now this meaning that, it means that if this is a resultant vector, I can transform it to the linear standard, or the standard basis, as nothing but x of B P inverse of x, right? So I can replace this A B of B, think of A B1 as x, so it means this is nothing but P inverse A times B1 and P inverse A times Bn. I can take P inverse A out and B1 up to Bn. This is nothing but again the change of coordinate matrix P, which is, remember from the earlier discussion, that this P is nothing but the basis with the following basis. So it means T of B is nothing but equals to P inverse A of P, P inverse AP. Now if you look at the similarity transformation, then A is similar to D when this exists. So if I do slight bit of mathematical manipulation and write this equation in terms of D, so you can see here this equation and this equation is same. means that T of B is nothing but equals to D. Okay. Now I hope you have now understood the real concept of what we have done so far. So it means, let's say, define, if we say define T r square to r square is a transformation in which T of x is equals to Ax, and A is 7 minus 4 2 and 1. You have to find basis B for r square with the property that beta matrix for T of T is diagonal, right? So we know that what we've been asked for us, this is A P D P inverse, right? So D we know that has nothing but uh, the eigenvalues here. The eigenvalues of this one is nothing but equals to, as we have done in our previous, so it becomes a determinant of A minus lambda I, and A minus lambda I becomes here as 7 minus lambda 1 minus lambda 2 and minus 4, right? When you take the determinant of this, which is uh, 7 minus 1 minus lambda, and you simplify that, the answer you get here is lambda 1 is equals to 5 and lambda 2 is equals to 3, right? And you can actually find out the corresponding eigenvectors, which is 7 minus 5 2 minus 4 and 1 minus 5. That leads to 2 2 minus 4 minus 4. So if you add, multiply by 2 and add them up, you have here x1 is equals to uh, minus x2, and so on and so forth. So it means first vector will become v1 is equals to 1 and minus 1. Similarly, you can find for lambda 2 is equals to through v2, which is nothing but equals to 1 minus 2. So the p matrix in this case will become as 1 minus 1 1 minus 2, and your D matrix will become 5 0 0 3, and D here is the eigenvalues here, and P is the set of the basis vectors here. Okay. Now uh, so we can do the another example to illustrate further the concept of this. So if I say, let's say A is equals to 4 4 minus 9 minus 8, and b1 is equals to 3 2, and b2 is equals to 2 1. So the characteristic polynomial that we have is lambda plus 2 whole square, which is determinant of a minus lambda I, uh, uh, so which is equals to lambda plus 2 whole square, and gives us the eigen value as minus 2 with the algebraic multiplicity of 2, right? Now the thing here is, uh, if you try to find the eigenvector corresponding to lambda minus 2, it will only have one vector, right? Because since it's got only one eigenvalue, so the multiplicity of 2, to actually have A being diagonalizable, you need actually two vectors. Okay. So uh, but here we cannot actually kind of use the similarity transformation, uh, but the thing here is, we've been given beta 1 and beta 2 the basis vectors, so we can use those basis vectors to actually first find the images here, which is AP as 4 4 minus 9 minus 8, 3 2 2 1, and minus 6 minus 4 minus 1, uh, and here, and then P inverse AP we can find easily, uh, equals comes out to be minus 1 2, 2 minus 3, um, and minus 6 minus 1, minus 4, and 0. This gives us basically minus 2 1, minus 2. So we can see here, if I use that, that your eigenvalues are actually uh, uh, on the diagonal, right? Uh, and the fact is, that supports the fact that uh, that A, uh, the matrix A, though not diagnosable at from the onset, but actually, if you if you look at it, right, uh, the thing here is you can actually find the non-diagonal matrix which corresponds to the beta matrix of T.